Good morning and welcome to the first of the ICCG webinar series on water. The topic of today's webinar is climate change, sea level rise and the importance of coastal wetlands. The International Center for Climate Governance was founded in 2009 as a joint initiative of Fondazione Eni Enrico Mattei and Fondazione Giorgio Cini. ICCG mission consists in disseminating science-based and socio-economic research in the field of climate change mitigation and adaptation, with the aim to define optimal governance models to control climate change. ICCG organizes international lectures, webinars, and workshops, and runs 3 interdisciplinary observatories on specific aspects of climate governance. As you may know, next year Milan will be home to Expo 2015 on the theme of Food Energy for Life, and in parallel, Venice will be hosting a collateral of Expo on Water Energy for Life. In this context, the ICCG has planned a series of 8 webinars during the whole 2015 on various aspects of the topic of water. Our speaker today is Professor Sonia Silvestri, who received her PhD in Environmental System Modeling at the University of Padova. Dr. Silvestri joined the Nicholas School of the Environment of the Duke University in 2011. The Venice Lagoon and its watershed have been her principal research sites in the last 15 years. I now leave the floor to Professor Silvestri for a half-an-hour presentation on climate change, sea level rise, and the importance of coastal wetlands. That will be followed by a 20 minutes Q&A time. So you're all welcome to send your written questions through the specific tool in the GoToWebinar. Probably not all the questions will be able to get an answer, but we will do our best. So thank you very much, and please, Professor Silvestri.
Thank you, Isabella, and I want to thank the International Center for Climate Governance for having invited me to give this presentation. I will start with some consideration on the sea level rise at the global scale. Tide gauges measurements taken in the last 50, 60 years have shown how the sea level has changed differently in different areas of the globe. As you can see from the slide, the West Pacific Ocean is experiencing the highest rate of changes, while the magnitude of changes in the Mediterranean Sea are smaller. This slide shows some gauges records measured along the coast of the North Adriatic Sea. If we want to focus on Venice in particular, we see that the natural subsidence is the first factor that we have to take in consideration. And as you can see from the slide, some areas of the city are sinking more fast. Some areas are sinking slowly. In general, on average, we might say that there is a natural subsidence of about 1 meter per year. This value has to be added to the sea level rise that has been calculated for the North Adriatic Sea, also based on the data on Trieste, which is about 1.13 meters per year. So we can say that the global relative sea level rise in Venice is about 2.1 meters per year. This is the rate that we'll refer to later on during the presentation. So what are the primary actions that we can take to try to contain the increase of the world temperature of the atmosphere? First of all, of course, is a reduction of CO2 emissions in general at the global scale. But another important aspect that has been considered in the last few years is the carbon sequestration. In the in this framework, coastal areas may play a very important role that I will explain during this presentation. As you can see, coastal wetlands are basically spread all over the world and all the continents except for Antarctica. These systems are characterized by soils that are permanently flooded. As far as as for the seagrass, for example, these areas are always flooded. Other areas like salt marshes or mangrove systems are flooded during high tides. These systems capture and retain large quantities of inorganic sediments, and at the same time the vegetation that develops on these environments produces a large amount of above ground and below ground biomass. Since the soil is almost always in anaerobic condition, the organic matter remains partially not decomposed and so is accumulated underground. To grow, plants uptake CO2 from the atmosphere, and the biomass of dead plants and roots is stored underground thanks to the lack of oxygen. As a result, thanks to the continuous subsidence of the wetland soils over time, this mechanism allows the system to sequester a large amount of CO2, creating a stock underground that is also defined as blue carbon. We can see from the plot on the right that there is a direct correlation of the organic matter accumulation and the soil accretion. From this slide, which is part of a study done by MacLeod et al. In 2011, you can see that the system is extremely efficient in sequestering carbon. The carbon barrel rate is in fact almost 2 orders of magnitude higher than the tropical boreal or temperate forest. As an example, if on average 1 square meter of tropical forest sequesters 4 grams of carbon every year, 1 square meter of salt marsh sequesters 200 grams per year. To quantify the global carbon sequestration at the global scale of coastal wetlands, we need to multiply the carbon barrel rate by the global area covered by salt marshes, mangroves, and seagrasses. So someone might think that since these areas are limited in their extensions at the global scale, then their global impact is probably small. However, in reality, as you can see from these tables, the actual global carbon barrel rate is absolutely comparable. As you see that, for example, for mangroves, we have between 31 and 34. This is due to the uncertainty on the global area coverage, while for temperate forests, we have 53 teragrams of carbon per year, so absolutely comparable. Another important aspect, an amazing aspect of these systems is the proportion of soil organic carbon compared to living biomass, so to the carbon that is stocked in the living biomass. As you can see with the tropical forest as a term of comparison, these systems can really mainly stock the carbon underground in the soil. So, as I've shown so far, beside the huge and well-known value of coastal wetlands linked to their ecosystem services, their ability of sequestering and stocking carbon is greatly valuable and has been neglected till now. So this is why we need to focus today on blue carbon conservation, and in particular about coastal wetlands, we want to focus on the preservation of vertical accretion, protection of the stocks, restoration of native wetlands, and eventually creation of new wetlands. So let's concentrate on how to preserve the vertical accretion. First of all, I want to present the mechanism that allow the marsh to keep up with the sea level rise. As you can see, if the sea level rise from this sketch, when sea level rise increases, if there is enough input of inorganic sediments and thanks to the continuous development of vegetation over the top of these systems, the marsh can grow in height. About the Venice Lagoon, we can certainly do some measurements and also develop models to better answer the question if the salt marshes will survive in the future. And I found this study made a few years ago by Day et al. That used a system to measure not just the deposition over the marsh, but also the global rate of elevation change. And as you can see from this study, especially for an area that is very stable, called San Felice salt marsh in the north of the Venice Lagoon, you can see that the rate of accretion is about 0.3 centimeter per year, and the rate of elevation is around 0. So we can say that this, from these measurements, this system seems to be pretty stable. Of course, the observation's gone on for just 3 years, so we definitely want to use a model to better understand the future of this process. Another source of information that is instead very recent from a researcher at the University of Padua, you can see that from these measurements, the soil organic carbon density is about 0.044 gram per cubic centimeter. So we can calculate the organic carbon stock in the first meter depth per square kilometers, and we see that this is 440 megagrams of carbon per hectare, which is 4 times higher than the stock in tropical forest soils, for example. Another calculation that we can do is to estimate the carbon sequestration every year, and this is more than 23,000 megagrams of carbon carbon dioxide equivalent per year. That is about the annual emission of 6,500 natural heating systems for a mid-sized house. So, as I mentioned, now we want to basically use these measurements to calibrate a model. And I'm reporting, for example, the model developed by Morani et al. In 2007, that where you can see that the change in the elevation depends on the deposition, on the erosion, and on the rate of relative sea level rise. It's a very, very simple model that allows us to describe what is the equilibrium. So basically, when the change in elevation is equal to 0, then we are at equilibrium. But the question is this equilibrium stable over time? And in what conditions is this equilibrium stable? So if we use the model and we consider a rate of relative sea level rise of, for example, 3.5 millimeters per year, and the concentration that is on average 20 milligrams per square meter per cubic meter, then we can find basically 2 stable states. One is at about -2 meter above mean sea level, below mean sea level, which is a stable state that is characteristic of subtidal platforms. Another equilibrium instead is, thanks to the presence of vegetation, is at about 30 centimeters above mean sea level. And this is the stable state characteristic of salt marshes. Small shifts from these situations will bring the system back to the equilibrium. But if we have strong changes in the variables of the systems, as for example, if we increase the relative sea level rise to 4.4 millimeter per year, keeping the same sediment concentration, then we still have the subtidal platform stable state. But the marsh stable state shifts to another stable state, which is lower than 0 meter above mean sea level, and this is the tidal flat stable state. So as you can see in this case, as the model predicts, if the rate of relative sea level rise is higher than 3.9 millimeters per year, then the marshes will evolve towards tidal flats, and we will not have carbon sequestration anymore, because of course carbon sequestration is there only if vegetation is there. Another important aspect related with the presence of marshes and the seagrass is for the Venice Lagoon in particular, is to protect the stocks. So the carbon that has been already stored underground. As you can see from this slide, one of the mechanisms that can make the stock decay is, for example, the lateral erosion. In this case, you can see that when we have storm surges, for example, the erosion might increase and might make the marsh disappear, and this creates a strong carbon release to the ocean. And of course, there is a lack of protection for the inland area too. Another mechanism that is unfortunately very important around the world is the land use change. As you can see from these slides, it has been estimated that the huge amount of CO2 released from coastal wetlands has an economic cost that is in total between 6 and 42 billions of US dollars per year. So this land use change increases enormously the release of CO2 to the atmosphere. About the Venice Lagoon, we can say that more than 60% of the salt marshes have been eroded or reclaimed in the last century, for a total loss of almost 5 teragrams of carbon. Luckily, over the last 23 years, the Venice Water Authority has acted to protect and restore several marshes, but similar initiatives have to continue in the future if we want to protect the carbon stock and preserve the capacity of our salt marshes to sequester CO2. Another important, extremely important stock at the global scale, stock of carbon at the global scale, is represented by peatland. Peatlands cover about 3% of the world land surface, and their degradation contributes about 66% of the total anthropogenic greenhouse gas emissions. So peat is decomposed by organic matter is composed by organic matter accumulated over hundreds of years in wetland environments. When peat is exposed to high concentration of oxygen, the organic matter starts to be decomposed and release carbon dioxide. The chemical reactions also creates a net mass loss and a consequent subsidence. In the southern basin of the Venice Lagoon, the Zennare basin is characterized by a very, very high presence of peats. So we have started a study about this. The area was historically a former lagoon, a former wetland colonized by Phragmites australis that stocked on the bottom and the soil a large amount of peat. As you can see from this slide, after the reclamation that went on between 1892 and 1966, the area started a pretty strong subsidence. And right now, most of the area is between -2 and -3.5 meter below the current mean sea level. In general, the problem is related with the use of this area, which is currently agriculture. We still have just one thin layer of 1 meter on average of peat around the basin, and beneath that we have a pretty deep clay layer that is not suitable for agriculture. So the area, when the peat will be completely oxidized, will become completely unproductive. Another interesting set of interesting measurements has been taken for a few years and correlates the soil temperature with the carbon dioxide flux and also the soil volumetric water content with the carbon dioxide flux. So can we use, using a model, can we use these measurements to project for the future what will happen in this environment? To explore the future behavior of the area, we used a model developed by Stephens et al. In 1984 that calculate the subsidence rate as a function of soil temperature, and we have seen that there is a strong correlation also from the measurements, and of the water table depth. The constants were calibrated using field measurements, and another model has been used to generate the future probability of the hourly rainfall events, and thanks to this we calculated that the mean subsidence, the future mean subsidence of the area is about 1.3 centimeter per year. Using this model, we also could calculate that the area has already lost more than 15 teragrams of CO2 and will lose even more, 17 teragrams of carbon dioxide if we do not act to protect the peats in this area. As a term of comparison, I can say that 17 teragrams of CO2 is twice the total stock of carbon in the Venice salt marshes. So the actions that can be taken to protect the Zennare basin are, for example, the restoration of native wetlands, and in case a creation of new wetlands. So to understand the possible cost benefits related with this restoration, we try to explore the few mechanisms currently in place that would pay say, landowners, managers, or governments to protect the carbon stored in this environment. First, we consider the no-action option. First of all, I want to say that this is a very recent result coming from the thesis of a student, Alessandra Cartage, that just finished her master degree at the University of Padua, and in collaboration with Professor Mario Putti, Professor Marco Morani, and also in collaboration with Enrique Dechen, who kindly accepted to follow this student for the economic part. So I'm basically presenting some of these results. So we considered the no-action options. In this case, the costs include the expenses for draining the area and maintaining the drainage system, plus the cost of CO2 emissions. In fact, and we make the assumptions that the farmers have to pay for the emissions. The benefit is the value of the land as a proxy for the economic value of the current use as agricultural area. The second option that we consider instead is the rewetting. In this case, the cost includes the expense of creating and managing protected areas, improving water quality, and the opportunity cost of the foregone alternative, which is, of course, in this case, the value of the land. The benefits in this second case, the rewetting case, are given by the avoided payment of the CO2 emissions. To estimate the economic cost of the emissions, we used the U.S. social cost of carbon document, which is the net present value of the economic cost of an additional ton of CO2 emissions. The three curves that you see are calculated for three different discount rates. So the results shows you that in the first hypothesis, we can see how the cost for maintaining Zennare drained, basically as an agricultural area, become higher than the benefits in the 2035 if we consider, for example, a discount rate of 3%. If we consider a discount rate of 2.5, the costs are already higher even today. Under the rewetting hypothesis, you can see that for both the 3% and 2.5% discount rates, the benefits are already higher than the cost. So it would be convenient to change the use of the area even right now if, we had a proper market for CO2 stocked by coastal wetlands. A final slide about rewetting of areas similar to the Zennare Basin is about the area in the Sacramento-San Joaquin Delta, which is in California. This area has undergone a strong subsidence due to reclamation, and in 1998 they decided to rewet the area, and here you can see how, of course, the elevation of the area started to increase. However, there is still an open question, and several scientists are working to get data about this. So we need still to better explore the emission of other greenhouse gases, as for example, methane, to understand what are the consequences of rewetting this area in terms of global emissions. And you know that methane is, for example, much stronger a much stronger greenhouse gas than CO2. But the current studies that I found around are not very clear. Certainly there is a strong importance, a strong correlation with salinity. So salinity really decreases the emission of methane, for example. So take-home concepts. The temperature has been increasing in the past century, and as has sea levels. We of course need to reduce somehow the emission of CO2, but also maybe invest in possible actions to sequester CO2. And in the salt marshes, seagrasses and mangroves are very efficient systems that should be protected to preserve the natural vertical accretion, to protect and restore them, and also through maybe rewetting of peat areas. So I want to thank you for your attention.
Thank you very much, Professor Silvestri, for this very interesting and very detailed presentation. We have a very interesting question from the public, and this is the following. What is the functionality in terms of carbon sequestration and conservation of natural marsh in Venice Lagoon compared to the artificial areas of reconstructed marsh, which are ecologically less diverse and also tend to be higher quota with refer to mean sea level?
Studies have shown that these artificial salt marshes, restored area, are slightly less efficient in storing carbon. Because of course it takes a lot of time for the vegetation to develop and of course increase the diversity in these areas. However, I do think that restoration is important, very important, and also in the case of the Venice Lagoon has greatly improved the quality of the marshes, and has also greatly improved the defense of the already naturally developed marshes. So because most of the time these systems, these new systems were developed in front of other natural salt marshes, so preventing the erosion of the natural marshes themselves. So I think has been a really valuable work over here, and will certainly give better results as soon as more vegetation can develop on these areas.
Well, thank you very much. I have a question, my own. To what extent the preservation and restoration of the wetland areas in the Venice Lagoon have helped to mitigate the risk posed by the sea level rise, and also to what extent do these kind of soft adaptation measures will help to increase the efficiency of hard adaptation measures such as the Mobile Gates project?
Of course, as I said, there is this great importance of sequestering carbon. From the point of view of actually having an impact on the high tides, I really like to think that soft measures are a good complement, even if they has been proven that they do not have a real effect in decreasing the high tides, as it can be the Moses system, for example, that has will certainly have the strongest impact. But soft measures are important actions to preserve also the quality of the environment and the quality of the water in a basin like the Venice Lagoon. So it is essential also for the survival of the marshes in terms of, for example, of allowing exchange of the water with the sea, and also allowing enough sediments in suspension, which is vital for the marsh to keep up with sea level rise. So I do believe that investing in these soft measures is really, really important.
Okay, we have another interesting question. So could you please briefly describe the Zennare case study? The question is, which are the economic activities that took part there, and do you consider how they will be affected by cost-benefit of the adaptation measures you suggest?
Yeah, so in this study, we only took in consideration the use, which is the main use of the area for agriculture. So the cost-benefit analysis was just related with the value of the land in terms of agricultural land. There are certainly other uses that can be explored to understand if, the future, let's say, lack of peat can affect the agriculture. We might, use other. We might change the use of the area towards other uses. I think that this hypothesis of converting the area back into the wetland might become more and more efficient in the future, and might give positive feedbacks, not just economically, but also of course, for the environment.
Okay, so we have another question related to the Zennare case study. So the question is, do you know whether public funding to farmers were also considered? Because often the main reasons to keep farmer coastal wetlands drained in agriculture, but this is a social cost through CAP and other funding streams. So do you know anything about the farmers?
Yeah, so the analysis that we did is basically based on the hypothesis that if the land is converted to wetland, then there will be a market of CO2, and the CO2 will be repaid by some public authority or by the European Union. So we basically, or by the private market, so just putting this CO2 onto the market and selling it. So basically this is the mechanism that we hope will be feasible in the future, since the CO2 market is already there, but till now no market is available for wetland areas. So that's also related with the fact that scientists are not yet sure they don't have enough data to assess other possible emissions, like, as I said, other greenhouse gases emission, like, as I said, methane. So once all these questions will be answered, then I really hope that a new market for CO2 from wetlands will be opened, and in that case it will be convenient for farmers maybe to change the use of their land.
Okay, thanks. Now we have a question from our researchers. Are there studies, works that try to develop future projections for carbon sequestered from wetlands and peatlands? And if yes, how projections been developed? Do you think this would be useful also for developing economic assessments of mitigation?
Yeah, definitely. Yeah, the studies that are at the global scale right now are mainly assessing, what the rate of carbon uptake from these environments, as you have seen during the presentation. But it would be, there are several groups that are working to better understand with models what will be the future uptake through these systems in different conditions. Of course, as I said, salinity plays a role, the availability of oxygen plays a role, and of course these systems are very efficient, but there is still a lack on the information of their real extension at the global scale. So it is really important to continue to do research in this field and assess with more accuracy all these details.
Thank you. Another question. Apart cost-benefits analysis, it is the case of other market instruments to promote wetland restoration. Especially the one who's asking the question is thinking of certification market as an example. So is there a case of other market instruments to promote wetlands restoration?
I'm not an expert. As far as I know, even here in the United States, there is a debate, there is a discussion, especially for peatland areas, to actually, assess the current extension and certificate this current extension of this area, and of course repay those that create new areas, or rewet these wetland, rewet these areas and recreate wetlands. Right now in the U.S., if you create a wetland, for example, they pay you for the decrease in the nitrogen and in the phosphorus that is taken by the vegetation that grows in these wetlands, but the carbon part is not clear yet. So I guess everywhere, also in Europe, I guess they are working to better assess this problem.
Thank you. Another question. So would you expect your analysis of the Zennare basin to change significantly should methane emission being considered? And also, could conversion into aquaculture be a more sustainable option?
Yeah, so I think, if we recreate a wetland with fresh water, then, for example, the emission of methane will probably be pretty important. And since, as I said, methane has a great power in terms of greenhouse effect, then the calculations will be definitely different. I think, you know, that the area originally was probably brackish water, which is water that has a medium, let's say, not too high salinity, but still is salted. And in that case, the emission of methane is really low, close to zero. So yes, I think that there is a lot of work to do to understand, you know, the difference if we use fresh or salted water, and in terms of emissions. You know, my idea is that if we recreate the natural brackish water environment, we will probably not have emissions of methane. What was the second part of the question? Yes, if the aquaculture. Aquaculture is certainly, you know, a use that provides a lot of money. But the thing is that only if you recreate a wetland, you can sequester carbon. So the thing is to evaluate what would be the gain of, you know, in terms of money, what would be the benefit of creating agriculture against, you know, the amount of money that they would pay for the CO2 sequestration. So if we pay, if the market will pay, you know, enough for CO2 sequestration, it might be more, you know, convenient to create a wetland instead that you know, an aquaculture system.
Thank you. So we have a question on temperature. Now, so you mentioned that temperature will also affect the ability of peatland to store CO2. So could you expand a bit more on this point?
Yeah, the temperature is a very important factor in terms of the CO2 emission. So at higher temperature, we'll have a higher release of CO2. And in the model that we have used, we have not completely, fully explored yet the change in the future possible temperature due to, you know, to climate change. So as I said, this is a preliminary study, and we hope to, you know, do more analysis for understanding also the future projections, so at higher temperature. Temperature is certainly an important factor, especially for the top layer of the peat.
Thank you. We have a question related to the sediment availability. So the question is, has the sediment availability in the lagoon changed since the work began on the mobile barriers of the Mosel?
I haven't seen any, you know, study about this. I think certainly during the work, probably the water turbidity has increased, but I've read a very nice study about, for example, the seagrass that develop in the south of the Venice Lagoon. They monitored the you know, the state of the seagrass, and we all know that seagrass are very much affected by the turbidity, and they monitor the seagrass during the works, and they have found no change. This is a study by the University of Venice. They haven't found any significant change in the, you know, in the population of these seagrass. And so yes, I guess the turbidity has probably changed or is probably changed during the works, but I think it's not a major effect of the MOSE on the environment, on the lagoon environment, I mean.
Thank you very much. Well, another question on subsidence. So the land reclamation increases the availability of O2 in the soil and starts the decomposition process. So how this effect has led to the decrease in soil mass and the consequent subsidence in the city of Venice?
The city of Venice, as we all know, is mainly developed on former salt marshes. When old Venetians started to build Venice, there were just a few islands. Most of most of Venice has been built on reclaimed areas, reclaimed salt marshes, basically. The thing is that these areas are in anaerobic condition all the time because it's underwater. So the availability of oxygen is extremely low, and the decomposition is also very, very slow. So that's something that happens mainly if you work the land, for example, for agriculture. But in the case of Venice, the natural subsidence is mainly related with natural compaction of the sediments. The strong subsidence that affected Venice has been related with the extraction of fresh water from the groundwater, from the aquifers, and impacted very much the city in the 60s and in the 70s, when the city basically sunk for 23 centimeters, considering subsidence and natural sea level rise. So that's the main reason for the sinking of Venice in the past.
Thank you very much. We have a last question for you on the economics. So do you think that future climate change, by reducing the economic value of economic activities that have developed at the coast of coastal ecosystems, could work in the direction of strengthening incentives to preserve some of those ecosystems?
Yeah, I hope so. I really hope that all these activities around the importance of sequestering carbon and sequestering CO2 will become an opportunity for our society to develop clever methods and valuable methods that might also be important for the environment. So I'm happy because today also also politicians are aware of the feedbacks of our actions in terms of acting on the environment. So this is certainly important for better understanding what will be the consequences of our actions, and important because the society now is more aware of how scientists can use their models to predict future consequences and hopefully not to do mistakes, too many mistakes.
Well, thank you very much, Professor Silvestri, for your very stimulating presentation and and comprehensive answers. And also thanks to all the participants, there were many really, and also for their very active contribution to the webinar. So I would like to remind you that the next 6th of March we'll have the second webinar, and will be related to the water challenges in the agricultural sector, and will be given by Professor Alberto Garrido from Universidad Politécnica de Madrid. So thank you very much, and we'll
Thank you.
go on the 6th of March. Bye-bye.
Thank you. Bye-bye.